day, because I don't know whether when you watch whether it will be good morning or good afternoon. So let me just say good day and let me start the talk. So, it's about a topic called invariants. So in mathematics, there are two types of research one talks about. One is something called theory building, another called problem solving. There are some people who just solve problems just for the sake of solving that problem. There are some others who just develop the theory and go and more deeper, and so that in turn gives more problems, and then you solve problems. You cannot strictly separate the two, but if we still think about this, like in Olympiad, for instance, it will be mostly problem solving, solving various types of problems. So puzzles often. So I was asked to give a lecture to Math Olympiad people, and I looked up some book on problem solving. So when you learn the subject, you generally just start with solving various problems. So there was this book, one book by Lauren, said problem solving two problems. So that gives you a list of various types of ways you can solve problems. So the various methods. So like one, it says search for a pattern. So that might give you a hint as to how to solve. Or you just draw a figure, okay, of the problem. So when, like especially some geometric type of problem, and instead of just thinking abstractly, if you draw a figure, it might help you. Then formulate an equivalent problem. Modify the problem. Choose an effective notation. Exploit symmetry. Divide into cases. Then work backward. So you start with the solution, think as to what has to be done to arrive at that. Okay. So then argue by contradiction. So there are many other methods, like then pursue parity. So 11. Consider extreme cases. And generalize. So often generalizing, you may get an easier method to solve, or you may get better ideas to how to solve. So these are the various methods suggested, but it doesn't mean that when you see a problem, you just try one by one. It doesn't happen that way. You just think about the problem and you typically strike, you get some idea, okay, maybe this works, maybe this works. But these are just suggestions. What I am talking about today is invariants It's actually a sort of generalization of this perceived parity. So I will explain it, the concept, by just solving some puzzles. Okay. So let us try to solve some puzzles. So the first problem, or the first puzzle, is from the book of Penrose, Roger Penrose. He's a famous physicist, famous for some solutions of tiling problems and many other things. So it is from one of his books. The book is titled Emperor's New Mind. New Mind. If you get a chance, you should look at the book. He says that we need to understand like our brains. If you want to understand cosmos, or if you want to understand space, because many things are determined on at a subatomic level, at a sort of quantum level, and the quantum theory is common. So anyway, the problem here is that you are given a set of equations. From that you have to derive something else. The equations given are, this I call as word problem. Word problem. So here the equations given: eat equals at. 8 equals A. Later equals low. Pan equals pillow. Car equals no. I hope you can read these equations. Eat equals at. So eat equals at, 8 equals 8, later equal to. So we are having words. So words means just a couple of letters. Okay. So these are given to you. So these are the axioms. So with that you want to prove theorems. So the first theorem, okay, you want to prove this. So theorem, lap equals sleep. So what is the idea? So these equations are given. So you can substitute. Like here there is an A, I can substitute A equal to ATE, like that. So the words do not have any meanings, just that these are the substitutions given. So from lap, you want to say that this should be equal to leap. So here is the proof. So lap, okay, you are allowed to do any of these substitutions. Like A is same as 8, so I can write this A, I can replace by ATE. So like this, you can go on doing substitutions. So now this at, I can substitute by eat. Again, I can this substitution here, 8 is same as A. So you see the words do not have meaning, but these are the substitutions I got. These are the axioms we believe. So with that, you can do any of substitutions. But 8 is same as A. So I can write this. Okay. So we have proved lab equals sleep. So this completes the proof. What we say quite easily done, right? QED. So here's it's a very simple theorem it was. So let me go to a slightly complicated theorem. not much complicated, but slightly a sort of longer theorem. Okay. So the theorem second is caterpillar equals man. Proof. Again, the same kind of thing. You go on substituting. So I will do it faster this time. So caterpillar so you do the substitution. I see in 8 I put A, 8 equals A, becomes car pillar. Then you substitute this A, becomes car. A is same as ATE. Okay. Now you substitute. Okay. This later is low. Excuse me. Now I can substitute this pillow. And that carp is and again you have to go another round. So mean, so here A is AT. Then it is at AT is A. So we have put it here. But you see it took much longer. So caterpillar, from there you go on doing substitution and you get caterpillar equals man. So now this kind of problems you can do with some trial and error. In fact, it would be much easier. You can just give it to a computer, and the computer can solve. Means each time it can see what are all the possible substitutions and go on doing substitutions, and you see that very quickly it will give you the answer. But this is not the problem I want to talk about. So I want to have a theorem now. Which claims the following. So I want to have the theorem carpet is not equal to meat. So what does it mean? It means that if you start with carpet, do these substitutions, anything you want. There are many ways you can do, like there is A, you can put A, whatever way you do. From here, you can never reach this. Or from meat, you do these substitutions, you can never reach carpet. Whatever way you do, it's impossible. Now, this you cannot give to a computer and ask to do, because if you give it to a computer, it will go on trying and it will never reach. Okay? But how do I show that you cannot go from here, you cannot go from here to here? So it is called non-recursive mathematics. So there is no algorithm. So earlier we had an algorithm. So from here, you want to reach here, you just try, various options are there, just keep on trying. Whereas here, you want to show that it is impossible to go from here to here. Okay, so that you cannot do just by trial and error. So how to solve this problem? So it is where this theory of invariance comes into picture, and what I will do, solve some other problems where the solution is simple, and then suggest you how to get this. So, but there is a, and this is, I think when it's a recorded thing, you have one option. There is, you can always put this on pause mode and try to prove it for yourself, this one, and then come back. It is not possible in a live lecture. So, what I want to do is solve some other puzzles where the solution is sort of obvious, much simpler, which you can see, and say that the same method works here also. So, okay, here is the problem 2, which I have called as sum game. So there are 3 people, A, B, and C. So 3 people are there, and A has 50 rupees, B has 100 rupees, and C has 200 rupees. Okay. So to begin with, A has 50, 100, and 200. So what is the game? So game can be anything. Or some competition they play. Okay. Then one of them wins. Okay. So in first round, whoever wins would get 1 rupee each from the others, from the losers. Suppose, okay, A wins. So then A would get 1 rupee from B, and he will also get 1 rupee from C. So this becomes 52, this becomes 99, and this becomes 199. Now suppose C wins. Okay. So then everybody gives 1 rupee, the others give 1 rupee to C. So the C wins, it becomes 200, this becomes 98, this becomes 51. Like this. So on the game runs. So every round there is some competition, something, one of them wins, exactly one of them, A, B or C, and the winner gets 2 rupees, 1 rupee each from the others. So on this continues for a long. So I want to say at the end, say all of them have equal 100, 100, 100. Okay. So if you are in the audience, you would immediately say, no, this is not possible. Why is it not possible? From 50, 100, 200. Some people go on playing. We are saying 100, 100, 100 is not possible. It's not possible because the sum of the total amount of money here is 350, whereas the total here is 300. So that's why, whereas the money total amount was constant, okay, it was not changing. This is what we call an invariant, something which is not changing. See, I didn't ask you that you should take the sum, but you yourself would take the sum and say the sum is not changing. The sum here, the amount of money the A has, the amount of money B has, the amount of money C has. Okay, if you add that, that is not changing each time. It stays as 350. So something which is not changing every time. So that is what we call an invariant. So here the sum is an invariant. The sum is not changing, so you cannot go to 300 from 350. Okay. So let me give you another example. So here, what we have is that we have 2 bags and a number of balls in these bags. So the bag 1 and bag 2. So bag 1 has some 25 balls. Bag 2 has 30 balls. What you do, say you toss a coin. Okay. Say, so if it is so head. Okay. You have some other balls with you. If it is head, you just add one ball each. Okay. So if it is tail, just toss a coin, see whether it's head or tail. If it's head, you add one ball each. If it is tail, then remove one ball each. So like first time, so I started with 25 and 30. Suppose you get head. Then you are adding one ball each, so it becomes 26 and 31. Then again say head, then it becomes 27 and 32. Then it is tail, say, then it becomes 26 and 31. Remove one ball each. Like that it goes. Okay, so you might ask, okay, if it is 0 and there is, I cannot remove, what would happen? So if it is 0, okay, head or tail, you just switch. Okay. You just interchange. Say 0 and some number is here, we just interchange. Like this, you go on playing. So what is the question? The question is, can we reach finally from here, go on doing, can I get 20 and 30? Again, if you think a little bit, you say that no, it's not possible. Because each time the difference is not changing. Okay? So difference 25 and 30, each time I am removing one each or adding one each or just switching. In any case, the difference between the two, it is always 5, right? So here 30 minus 25, 31 minus 26. Like that, if I look at the number of balls in one and the number of balls in the second one, if I see the difference, if you want, you can take the modulus. So that is not changing. Okay, so difference is an invariant here. So it is not changing. So each time the difference has to be kept 5. So from 25-30, you cannot reach 20-30. Okay? So that is it. Okay? So this is simple. So let me go to the third problem. It requires a little bit of thought, but if you have seen it before, it's okay. Okay. So the third one is a number game, or I will say numerology, or number game. So idea is that so you start with some number, okay? Natural number. Say I started with 3, 5, 7, 1. Okay? So some operations are allowed each time. So what are the operations allowed? One is that adding parts. Okay? So like 3, 5, 7, 1 is there. So if I want, I can add 35 plus 7. Okay, so it gives you 42. So this will become 4 to 1 because I have just added 35 and 7. So you can do like this. You can say I can add 4 and 2. It becomes 4 and 2, 6. So it becomes 61 like this. So this is one step allowed, adding parts. Another, you can do the opposite thing. You can decompose them. Okay, into parts. So like from here, 6 is 1 plus 5. So I can go. This is like this. You can decompose. So you may add the parts. You may decompose the parts. And the third thing is you may permute. Like this 151, I can make it 511 if I want. Okay, so permute. Okay, so 3 types of steps are allowed: adding parts, or decomposing them, or permuting them. So like this, you go on doing. So here is a question like this. So there are many different ways of doing it. Right? Each time you can do it many different ways. So, but the question here, from say 2, 4, 5, 8, it is possible to go to 1, 1, 0, 8. Okay, it's possible. But from here, this is not possible. Okay, not possible. Which one? 1, 1, 0, 9. Not possible. So how do I say something is not possible? Okay. So this one, which is possible, what you do, you have to just divide it and like this and arrive at this. Whereas not possible, how do you show? Okay. Just by this kind of trials, you cannot say that it is not possible, because maybe what you have tried is not enough. So if you have done work with numbers for some time, you will see that any of these steps keeps the remainder when you divide by 3 unchanged. It is an invariant. Okay, so the invariant here is the remainder when you divide by 3. So like here, you can see what is the remainder. 2 plus 4 goes away. This gives you 2, this gives you 2, this gives you remainder 1. So here, whereas the remainder is 2, okay, when you divide by 3, right? So, so here the remainder is 1, here is 2, so it is not possible to go from here to here. So remainder, when you divide by 3, is an invariant. See, in the problem, nowhere 3 is mentioned or the remainder is mentioned, but you just think of that, okay, this works. Okay. If you are looking at the remainder when you divide by 3, it is not changing. Okay. So this kind of thought, okay, you have to do this. So that is your brain which is doing, and it's not something which can computer think of easily. Okay. So now what I want to do, I want to formalize this method. Okay, what exactly we are doing in this, all this. We are coming up with some formula and saying that this is an invariant. Okay. So this is the method of invariance. So what is it? So let me explain. So what is the setup? The setup is you start with a set. No, it's just a collection of well-defined objects. So the set depends upon the problem you have in, like the initial problem where there were 3 people with a certain amount of money each. So the amount could be any number. Okay. So I can take, if you are allowing negative money, I would take integers like this. If you are allowing only positive money, you can take this as the collection. Okay. The triples of numbers were the set here. When you are talking about the second problem, there were just 2 numbers. Okay. So then it was z cross z. Actually, it was number of balls, so it cannot be negative. So maybe I can take z plus the positive numbers or the whole numbers like this. So that, and the third case, just we had just this one natural number. So this. So you have a set where the action is taking place, where things are changing or you have the dynamics, things are moving. So that is the set. Okay, some set. Okay, so then we write, okay, x, read it as x is equivalent to x. Okay, so when you go from one step to another, if you want, you need not change the element. You may keep it as it is. Okay, so that means no change. Okay, you just keep it as it is. You start from x here, and the next step it is x again. Okay, that is allowed. So what this is saying, that you may go from x to y, then you may go from y to x. Okay, like here you do the change, from x, after some steps you go to y, then you should be allowed to go from y to x. So the rules of the game should be like this, is we are prescribing for this method of invariance to work. You are allowed to stay at x. If you can go from x to y, then you can go from y to x. And the third one, if you can go from x to y, and if you can go from y to z, this implies you can go from x to z. So because from x, after some steps you reach y, from y you can go to z, so after some steps you reach z. So this means from x you can also go to z. Okay? So this is something what we call an equivalence relation. So we say x is equivalent to x is equivalent to y, implies y is equivalent to x. So this is called reflexive, this is called symmetry, this is called transitivity. So what we are assuming is that you are starting with a set S, and you have a game where the rules allow you just stay at x, or if you can go from x to y, you can go from y to x, or the transitivity, if you can go from x to y and y to z, then you can also go from x to z. Okay? So this is an assumption that the S has this kind of relation. Okay? Equivalence relation. So what happens is that once you have an equivalence relation on a set, so here is set S, look at x, look at all the things equivalent to x. So you put into one group the things equivalent to x. Okay? So which is called the equivalence class of x. Now you look at something which is not in this class, then you look at its equivalence class. That will not intersect with this, because if there is something here which is equivalent to both x and to this, then it will be in the same class. Okay? So any equivalence relation divides S, or the partitions S, into equivalence classes. Okay? So it is very general. It can be any set, any equivalence relation. Any equivalence relation would partition S into equivalence classes. Okay? So now what is an invariant? An invariant, okay, on S, given this equivalence relation, is a function f on S such that x is equivalent to y implies f of x equals f of y. So I didn't say where this function is taking values. Okay? It doesn't matter really. So, but for now, let me take the function as, say, taking values in numbers. Okay, set of natural numbers, say. Okay, it doesn't matter. Later on we'll change it. But at the moment, say the function is taking values in natural numbers. So what we are saying is that we call it an invariant. If x is equivalent to y, then the value of f should be same. Okay, f of x should be f of y. So within the same equivalence class, the function should take same value. Okay, so this okay, inside this. Now if you take another equivalence class, the function may take the same value or may be different. We are not saying anything. Okay, but within the same equivalence class, f of x should be equal to f of y. If x is equivalent to y, f of x equal to f of y. Okay, so in other words, if you can go to y from x, then f should not change. F at y should be same as f of x. This is precisely an invariant. This, if you remember the three games we looked at, three puzzles. The first one was three people A, B, C having 50 rupees, 100 rupees like this. Then the sum was an invariant. If you have three numbers here, A, B, C, the value, the amount, then you take the total. So that was an invariant. Okay. Whereas for the second game, which we had the bags like this, the problem 2. So then I had an invariant which is the difference. Okay, A minus B modulo. See there, if you take the sum, that will not be an invariant because you are adding one ball each or removing one ball each. So the sum will not be an invariant. Okay, whereas the difference is an invariant. So what is an invariant depends upon the game, depends upon the problem. But if you come up with an invariant, what you can say is that, okay, if you have a start with x and you get y, you can evaluate this f of x and f of y. Suppose f of x is not equal to f of y, then you can't go to y. Go to y from x. So if f of x and f of y are different, then you cannot go to y from x. And that is precisely what we did in each of these games, right? The first one, you looked at the sum and said, okay, here the sum is not changing. So from 50, 100, 200, you cannot go to 100, 100, 100 because the sum has changed. That is not possible. Same way in the second game, you got a different invariant. In the third game, also you got the remainder when you divided by 3. But there are certain things to understand there. Like the number game, for instance. If I start with, say, I start with 35. From this, you see whether you can go to 2. You see the remainder is 2. This, well, let me, well, I am dividing by 3. So the remainder here is, so this is 2 mod 3. So, okay. So my invariant here is you divide by 3 and look at the remainder. Okay. Now what I do, sometimes even though it has the same remainder, it may not be possible to go there. Okay. So because what this is saying is that if the remainders are different, then you cannot go from one to another. But if the remainders are same, your theory doesn't say anything. Because for instance, I can even take just a constant function, the function which is same everywhere. That would be an invariant. But it's an useless invariant. What you want is an invariant which works, right? So for your question at hand, it should tell you whether it's possible or not possible. So sometimes, here, for instance, I can, it is possible sometimes this function is so nice that x is equivalent to y implies and implied by f of x equal to f of y. If I have such a thing, it is more than an invariant. It's a what we call a complete invariant. Complete invariant. Okay. So this just means invariant. X is equivalent to y implies f of x equal to f of y. X is equivalent to y if and only if f of x equal to f of y. Then this is called a complete invariant. So if I have a complete invariant, then I can detect completely whether it is possible from x to go from x to y or not, just by the value of f. If they are equal, it's possible. If they are not equal, it's not possible. What I wanted to say here, the complete invariant here is when you divide by 9 and look at the remainder. Divide by 3 is not good enough. Okay, you think about it. You can solve it for yourself. That dividing by 9 and seeing the remainder, you get a complete invariant. Whereas dividing by 3 and seeing the remainder is an invariant but not complete. So typically, it is much harder to get complete invariants. Whereas you, with some effort, you get an invariant, and that gives you the job. It means solves the problem for you, for the problem at hand. Okay. But it's much better, of course, if you can get a complete invariant. Now I can solve the first problem, the word problem. So the word problem which we are doing, the Penrose word problem. So So what was the set S? Set S is the set of words, right? The tuples of letters. Okay. So that is the set S. So I have to define an invariant on that. So f of a word, okay, we define, okay, f of a word as number of A's plus number of M's plus number of W's. Okay. So this is f. I claim that number of A's plus number of M's plus number of W's. So I claim that this is an invariant. Okay. For that you have to go back and see the problem. Right? We had eat equals 8. Now what is f of eat? To count the number of A's plus number of M's plus the number of W's. There is only one A, so f of eat is just 1. And f of AT, again if you count A's, M's and W's and add, it is just 1. Okay? So whenever you do this substitution, you are not changing the value of f. And you can see for each one of them, AT equal to A, f is always 1 here, t equal to 1, like this. Okay. So almost all of them, maybe there is one place the number is 2. But what is important is that the value of f in each of these substitutions is equal. So whenever you do the substitution, you are not changing the value of f. Okay? And we wanted to show carpet not equal to meat. Now if you compute f of carpet, that is 1, whereas f of meat, that is 2. So from here, you go on doing substitutions, never the value of f changes. So there is no way you can reach meat. Okay, so that is the rule. Okay, from here you cannot go here, from here you cannot go here, because the substitutions do not change the value of f. F is an invariant. So as soon as you get an invariant where the values are different, you know that you cannot go from here to here. Okay, you may get here something value f is same as 1, then you can't say anything from here. Okay, from this theory, what you can say is that the value of f are different. You cannot go from one to the other. F, the number defined like this, is an invariant. How did we come up this? Well, that depends upon the problem. You have to look at the problem and see what works. Okay, you have to choose the f carefully so that it doesn't change in the substitutions, and here it should be different. Okay. So you have to do your thinking to come up with that. So here is a problem which Terence Tao discussed. I will not give you the solution, but just give you the problem. So there is, in this problem, there is certain island, okay? In that island, there are these chameleons, which can change their colors. So there are 13 gray chameleons and 15 brown chameleons and 17 crimson chameleons. So there are 3 different colored chameleons. So what happens? So when these two chameleons meet, suppose a gray chameleon and a brown chameleon, 2 of them come together, then both of them would change the color to the third color. Okay? When 2 distinct colored chameleons meet, both of them, they change to third color. So like if a brown and a crimson colored chameleons come nearby, then both of them become gray. Like that it goes on. Okay. So this is the game. So in this diagram, the 13, 15 and 17 like this. What is the question? Question is, after some time, is it possible that all of them have same color? Okay. Is it possible that all of them have same color after some stage? Well, you would guess that, okay, it is not possible, but then you have to get an invariant, okay, which works. Okay. Just the sum will not do, because the sum would remain same, because only the colors are changing. So you have to come up with a different invariant. Okay. Now, get to two other puzzles which are solved in a similar way, and you may have seen some of them, sort of popular ones. Puzzle 6 is a chess game. So you have a chessboard. So like this. So it is 8 by 8 cells. Like this. And what is that? Initially removed one at this corner, and this has been removed. Okay. So in the same way, at this end, one has been removed. Okay. So then, I have not done 8 by 8, you do it. Okay. 8 by 8. So one cell here has been removed and one cell here has been removed. Then, initially we had 64. Now you have only 62. Okay. And what we have is a 2 by 1 pieces like this. Small pieces with which you want to cover here. Like you put here, then here, then here, then this one you have to put like this, like that. You with 2 by 1 pieces. So how many you need? You need at least 31 of them. Okay. So to cover 62 cells. So with 31 of these 31 pieces, whether we can cover this chessboard with 2 extra cells removed, okay, 2 corner cells removed. If the corner cells were there, then obviously you can cover it. But with this removed, you have to do a little bit of thinking here, you have to put it the other way around, like this, you have to go on. So whether it's possible or not. Okay? As I said, some of you may have seen this problem, and it is not possible. And how do you do it? You see each time this is a chessboard, it is colored black and white, right? So you see each time this one, wherever you put, it will cover one black and one white, wherever you put. So if you count the number of black squares covered, so you cover some things, so F of that, what is number of black cells covered, okay, any tiling, you see the number of black cells covered minus the number of white cells covered. Okay. If you see that difference, that has to be 0 all the time. Okay. So whenever you put an additional piece, you would put equal number of black cells and equal number of white cells gets covered. Whereas when you remove these corner things, you remove the things of the same color. Okay. If this is white, this also would be white. So there is a difference in the number of black cells and the number of white cells. But whereas whenever you cover here, this difference is always 0. That's an invariant. It won't change. If you go on putting additional block, it will not change. You put some or remove some, it will not change. Okay, so that is the invariant. So that gives you the answer that it is not possible to cover this chessboard with 2 corner cells removed with this kind of 31 pieces. There is another puzzle which became very popular at one time, much before the computers came, of course. And it's called the 15 puzzle. 15 puzzle. So it's like this. You can Google for this 15 puzzle and get the history of this. There was someone who gave declared money for solving the puzzle. So you have 16 like this, 4 into 4. And these are numbered. You have pieces here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Only thing is this is empty. Okay, this piece, there is no piece here. 14, 15, that has been reversed. 15, 14. Okay. So what you do, so this space is empty. So you can move these pieces from anywhere, like you can move this 12 here. Okay, then this becomes empty. So there you can move either 11 or 8. Say you move 8. Say then this becomes empty. Then you move the 7. Like that you play with that game. And there is one space empty for you to have that freedom of moving. Then the puzzle is that from this you start and you have to end up finally with the correct order where you have 14 and 15. Okay, whether it's possible or not. Okay, so basically you are just permuting these numbers. 1 to 15 are there. You are just permuting them, and you want to end up with the right permutation, 14, 15. Okay, and not very surprisingly, it is not possible. Okay, otherwise one would get with some trial and error, but it's not possible. So once you say that it is not possible, you have to get an invariant to say that okay, it is impossible. Why it is impossible? Okay, because you cannot keep trying all the time. Right? You cannot exhaust the number of trials. So idea is that there is the parity, like the previous one. So the permutations are divided into odd permutations and even permutations. Okay, so like one transposition, one you have 1, 2, 3, 4. You change at one place. That is an odd permutation. If you know about matrices, there are permutation matrices. You see the determinant is whether +1 or -1. So that decides whether it's an odd permutation or even permutation. So here, this is an odd permutation, and you see that if you work it out, every movement keeps the oddity. Whereas the original one is an even permutation. So you cannot go from the odd permutation to even permutation. These moves don't allow that. So that value, whether the permutation is odd or even, you can give the value +1, -1, or 1 or 0, whatever it is. That gives you an invariant. Okay. Now, one more puzzle. Okay, some useful things, because they are so far all real puzzles. So here is one thing which you can check for yourself. So many books, you would see at the back there is a number called ISBN number. Okay, so it's a number given by publishers, some international society. So here is one example of some book, that book of Penrose I quoted, the ISBN number of that. So the ISBN number identifies the book. Okay, if you say this is the ISBN number, you see that you can search and you see that this is the number of the Penrose book. Okay, so what you do with this ISBN number? So just you multiply the. So there are 10 of them, D1, D2, D3 like this. So D1 you multiply by 1, D2 you multiply by 2, D3 you multiply by 3, like that you multiply. Okay. So finally up to 9, D9, up to here you go. Then you take the remainder, okay. Sorry, right? This when you take the remainder, you will get the, when you divide by 11. Okay. Divide by 11, you add this d1 times 1, 2 times d2, 3 times d3, add this up to all the way up to 9th one, and then you divide by 11 and you look at the remainder, this you will get. So you can say for this, the remainder is an invariant, it should this, or this minus this, the remainder should always be 0. Okay? So they have given the numbers like this. Why is that? Why did they do that? The reason is that when you convey the number, sometimes there might be a mistake. Instead of 1, you give 2. Then, see, the formula will not work. That you immediately detect that there is an error. So it is what's called an error detection code. Okay? So you are given it so that a formula like this, which you can, the library can always check. You can have a computer set this to check this, so that if there is some small mistake, the computer can detect it. Of course, if you make a mistake and you end up with the ISBN number of another book, then you cannot detect. But the small mistakes, mistake at one spot or just interchanging, it can detect. And that is done again by invariance. So this minus this remainder should always be 0. That 0 is invariant, it should not change. Okay? Well, this is old ISBN numbers, they are 10-digit numbers. Then now the 13-digit numbers have come and they have a different formula. You can look up Wikipedia as to what is a different invariant. There is a different formula. So each time you ensure that this minus something, remainder something is always 0 or always 1. Some formula is fixed. Okay? So if there is a change in that, if it doesn't satisfy the formula, then you know that there is an error, there is a mistake. Okay? So ISBN codes, they adopt that strategy. It is not just ISBN. There are many times when you send a message, everything, the things are coded, and then there are error correction methods. So where you make some copies and you see that something has to be satisfied. Even with these barcodes and everywhere, there are detection methods. Okay? If there are small errors, it should be possible to detect them. Okay. So next I come to another invariant, which is completely mathematically useful thing, something called Euler characteristic. Very famous invariant called Euler characteristic. Okay. So this is about, well, there are many generalizations. I am talking about the simplest one. You just look at a graph like this. Okay. So what is a graph? You take some vertices, okay, then you connect them by edges. Okay. It is, you may think of like towns, and they are connected by roads. So these are towns. So these are called, so we call it a graph. So vertices and edges. Okay. So these are vertices 1, 2, 3, 4, 5, 6, and they are connected by edges. It doesn't matter how I join this, whether I join like this or this, doesn't matter. What matters is like there is a road between 1 and 2. It doesn't matter how it goes. Okay. Like that. And I'm taking the simplest things like this thing of connected graphs. I don't take something separate, and also I'm drawing it on the plane. Okay, what are called planar and connected graphs. One can generalize, but let us take the simplest. So here, I want to add one vertex, one edge, like that you can go on doing. So what is the Euler characteristic? So E, and so on. So this is actually, I just write it as formula. B minus E plus F equals 2. So this is the formula. Euler characteristic is this, B minus E plus F. That should always give you 2. Okay. So, like here you can check what is the number of vertices. 1, 2, 3, 4, 5, 6. Number of edges. 1, 2, 3, 4, 5, 6. Okay. And what is F? F is the number of phases or the number of regions. But inside region and outside region, both are counted. So here there are just 2. Okay. 2. So here you see 6 minus 6 plus 2, you get 2. So V minus E plus F is always 2. Okay. You can add here one more thing. So like this. Then you see the number of vertices has increased by, so now number of vertices is 7. Number of edges that has increased by 2, but number of faces also increased by 1. So again you see this formula is 2, V minus E plus F. So this is an invariant of what? It is an invariant on the plane. Okay. On the plane, you add vertices, remove vertices, add edges like this, always this will be satisfied. So in other words, if somebody gives you a large number of, say number of vertices will be 1000, number of edges will be 999, something he gives, and unless this formula is satisfied, it is not possible to find a planar graph with that many vertices, that many edges, and that many faces. Okay, so it's a property of the plane. So it is each time you see, if you try it out, you see, add one more vertex, edge like this. You try it out, you see that each time this formula is retained. It has many generalizations. It's very important concept in topology. Like as I said, this is a thing about the plane. You can also go to cylinders, the number changes like that. So it allows you detect which space you are in. Okay, so it is an important mathematical concept. So Euler characteristic is an invariant. Mathematically very useful invariant. Okay. Here is another one. So I said initially, but so far I think we have taken all the invariants we looked at are just numbers, but it is not necessary that they are natural numbers. It can be real numbers, it can be complex numbers. In fact, in mathematics you go much further. You can have algebras. For the invariant for them can be groups. For invariant for groups can be algebras, or you can have polynomials. Anything, means any mathematical construction actually. There is no restriction. You just have to. The main thing is that it should be possible to compute them, and it should be possible to distinguish them using the invariant. So the invariant should be computable at least in the easier cases, and it should help us to decide. Okay, that is the idea. There is no restriction that it has to be a number or any such thing. It can be any mathematical structure. Like we have a thing called K-theory of C-star algebras, where you associate groups to classify C-star algebras, or even to classify topological spaces, one attaches groups. Sometimes you may attach, or by attach I mean you have invariants, which are groups or which are algebras like that. Things is possible. So I'll give you one more example. Here it is a polynomial, like real polynomial you take quadratic. Ax square plus bx plus c is a polynomial of quadratic. Now you just change. Okay, you have this function here. Then you change. You get translated. So you get a into x plus d whole square plus b into x plus d plus c. Now you get something, say, if you simplify this, you get some ax square bx plus c, say. So in this quadratic, you have moved it slightly. So, but the coefficients change. Okay. But if you see the number of real roots, etc., that doesn't change. So you need an invariant. Okay. So here, if you see that what is known as the discriminant, which is b square minus 4ac. Okay. So you see the b square minus 4ac here, and if I shift it and you have new coefficients, you compute the same thing here, they are not changing, they are same. So the discriminant is not changing. That is an invariant. So like this, there are many invariants, useful invariants. So, okay. Another famous one. Here. Suppose we start with a square like this. So it's a piece of paper like this. You cut and rearrange it. So cutting and rearranging, can I make it bigger? You cannot make it bigger, right? Cutting and from, so this has 4 as the, this is 9. So if the area here is say 4 centimeters square, here is 9, it is not possible. You say area is an invariant. If you have a piece of paper, you cut and rearrange, the area cannot change. Right? So I am not even saying that you should cut like this. You may cut it like this and then rearrange. It is still not possible to go from here to here because the area here is different from the area here. The area is not changing. Area is an invariant. Okay? Now, there is a funny thing here. Okay? As to what is area? Okay? Like when it's a rectangle, you say its the area is the length into breadth. Okay? So you need to know what is the length. That is also a big problem. Like what is the length? Suppose you have a river, like this, say a river. What is the length of the river? It is not the distance from here to here, right? That would be much smaller. The length, you have to go like this. So, how do you measure the length? So, if you have a string, you may sort of put it here and then straighten it out and see, right? So, that means you have to go along like this, okay? So, that means from here, you say that if you just measure like this, it won't give you the length. Instead, say you have to divide it into small pieces and look at these lengths and add them up, right? So you are approximating the length. You try to sort of straighten it out and then approximate. Same thing to do with area. If you want to find the area of this, you divide it into small rectangles, okay? And for the rectangles, you know the area. Try to approximate. So this is how the area works or the length works. So if the river is really bad, the length can come out to be infinity. Because if you try to approximate, you see there is no reason why it should converge. The same thing happens to area. There are portions, the regions which is really crooked, then it may not be possible to define an area. The area might become infinity. Okay? This very funny, means it might look strange, but it is true, and there is something called Banak Tusky paradox. See, what I want to say, the simplest case, say, suppose I take the unit interval, 0 to 1, and then I take, say, the unit 2. So, if I ask 0 to 1 interval and 0 to 2 interval, which has more number of points? Most people initially would say, oh, this has more number of points. But that is not true. This and this have same number of points because for any x attached with 2x, like half goes to 1. So this x goes to 2 times x. So then, if you count x, I will count 2x. Okay? It will cover, whenever you are covering the 0 to 1, I am covering 0 to 2. So this interval and this interval has same number of points. And that happens. So, but this is infinity. What if I do with finitely many things? So Banak Tusky paradox says that you take a ball, say a ball of gold or something, a unique ball. You cut it into few pieces and rearrange, and I can get 2 balls of same size. Okay, not smaller size. Okay. So that looks very strange because this contradicts this kind of thing. Because you had a certain volume here, you have double the volume. Okay, just by cutting it into few pieces, say 5-6 pieces, and arranging, just rearranging. I am not expanding them or anything, just moving them and putting it back. So why this argument, the volume is an invariant, why is it not working? It is not working because the pieces which you get here in their construction, they are so crooked, there is no volume for them. It is not possible to define volume from them. And so because of that, when I cut this and I move this, these individual pieces, they have no volume. So I cannot say this volume is same as this volume. So finally you put it in this way, it has volume. It is 2 times this. But here there is a volume. But in between pieces, they don't have volume. So because of that, the invariant thing doesn't work. So it is indeed possible to divide a unit sphere into few pieces, not infinitely many, just a few pieces, move them without expanding or anything, and get 2 of them. Okay, you look up this Banak-Tusky paradox. There have been many such problems. One of them, of course, where you don't want to cut like this, but you just want to cut with scissors, you want to cut with straight lines, okay, or polygonal lines or straight lines. Okay. So then there was this problem, like you start with unit cube, okay. Unit cube like this. Then you want to go to the tetrahedron, okay, with the same volume. So you cut this into pieces, okay, not that kind of ugly pieces, but with straight line edge pieces, okay. And from cube, can you go to tetrahedron? That was a question. Okay. So these pieces in between, they will have the volume, everything. Okay, there is no problem because it is a nice pieces. You just cut with scissors, whether it's possible or not. And it was seen by Den that it's not possible. So, and he came up with an invariant called Den's invariant to show that it is not possible. The volume remains same. The volume doesn't work as it's not good enough to distinguish. Okay, the same value. But Den's invariant is something very complicated mathematical concept. Again, you can search in the internet and you can get. Here is a sort of somewhat accessible explanation of this Den's invariant, Chris Schwartz, which explains this invariant. Okay, just going slightly beyond the volumes, an invariant which distinguishes this and this. Okay, so there are elementary problems where it is still hard to get invariants. Okay, the invariant is not something very simple here. It's quite complicated actually. Covered everything. I just want to say here, sometimes the invariants can be quite crazy. There was John Jones. He found some invariants for something called subfactors, some algebras, subfactors. He found the invariants. Those invariants were numbers, but those numbers were taking only these values: 4 cos square pi by n greater than or equal to 3. These numbers, as well as this interval, 4 to infinity. Okay. These numbers you see there from here is equal to 4. There's just some numbers, discrete set of numbers, and then the whole interval. These are the values taken by this invariant, the Jones invariant for, it's called Jones index for subfactors. He also found another invariant for knots. You know the knots, you just try the strings like this. For knots, we found an invariant. Like the knots, you are allowed to move the things, but you are not allowed to cut across like that. So it's called Jones knot polynomial. Okay. So for that, he got the Fields Medal for these two work actually. So, okay. Finally, to more or less end the thing, my talk. Just want to put you one problem. See this, as Penrose said, this kind of invariant is not the computers can think of. We think of the invariant for the problem and solve it because it is not algorithmic. So you need some intelligence. But these days the computers have something called artificial intelligence. They can detect the pattern, so you ask them to detect the pattern. But still there are problems which not even computers are able to solve. So want to say we are in this COVID times. I want to remember this name, Conway, famous mathematician. See the virus, if something is shown to us, is that we have to depend upon science, only science, the scientific methods, and everywhere mathematics plays a role. So one is the impressive growth of the virus, the way it spreads, the exponential growth, right? The exponential growth, the way it goes. See that is, you may have seen this problem, again, you take the chessboard, in the first cell you put, say one, grain of rice. In the second one you put 2, and the third one you put 4, then 8. So you keep on doubling. Then you see, you want to fill, it goes up so fast just by doubling that you want to fill up one chessboard. All the rice you have in India will not be sufficient. Just cover one chessboard because the growth is so fast, the doubling rate. So that same thing happens with the virus. If it keeps spreading fast, like if it doubles in every day, then within a month it can cover the whole world. So the same thing happens with these locusts also. They double so fast, the growth rate is so fast, the exponential rate is what is happening. Okay. So Conway studied many of these things, the way the organisms go, they mutate, and everywhere the role of mathematics is clear. And unfortunately he died recently in April. He is famous for this called Game of Life, which tells about how these things go, how things mutate. And he died in April because of this COVID. So I want to end with a problem by him. Okay. The problem is simple. Okay, you start with a number. Okay. Say I start with 10. Then you from 10 you will go to 30. How? Like this. This is 2 into 5. You will go to 3 into 5. Like this. So the number. So here is the general prescription. If the number is of the form 2k, then you go to 3k. If the number is of the kind 4k plus 1, the 2k goes to 3k, so it becomes larger. But if it is the number is of the kind 4k plus 1, then it will go next to 3k plus 1. And if it's the number is of the kind 4k minus 1, it will go to 3k minus 1. Okay? So let us do an example. So I start with 4. So the 4, so this is 2 into 2, so it is of the kind 2k. So it will go to 3 times 2, so that is 6. Okay. Now 6 is again 2 times something, right? It is 2 times 3, so it will go to 9, 3 times 3. So you are at 9 now. 9 is 4 into 2 plus 1, so the k is 2. So it will go then 3 into 2 plus 1, 7. Right? k is 2 here. 4 into 8 plus 1 is 9. So you do 3 into 2 plus 1, 3 into 6 plus 1 is 7. Now 7 is again it's 4k minus 1 type. Okay, 4 into 2 minus 1. So I will take 3 into 2 minus 1. So I will get 5k. So 3 into 2 minus 1 is 5. Now 5 is again of this kind, 4k plus 1. 4 into 1 plus 1. So I will get 4 into 7, 5. It's 4 into 1 plus 1. So then it will go to 3 plus 1, right? So it goes to 4. So where does 4 go? You do the computation, then it will go to 8. It has gone to 4. Okay. So this is what I wanted to say. We started from 4. It ended in 4. So then again it will repeat, right? 6, 9, like that. So you started from 4. You do this algorithm. So whenever it is of the kind 2k, you go to 3 times k. If it's 4k plus 1, you go to 3k plus 1. 4k minus 1, you go to 3k minus 1, like this. Okay, what are we doing? So what are we doing? So the set of natural numbers you have, 1, 2, 3, etc. We have this function. Okay, so g of n equals 3k if n equal to 2k. 3k plus 1 if n equal to 4k plus 1. Okay, is 3k minus 1 if n equal to 4k minus 1. So we are applying this function g, like g of 4 is 6. Okay? So you have the set of natural numbers, you apply g. Okay, you start with an n, then you go to g of n, then apply g again, you will get g square n, then g cube n. These are called the orbits of g. So you say x and y are in the same orbit if you can go to y from x or from x to y, right? X and y are equivalent. So this is are in the same orbit if y equal to some g to the m of x or x equal to gn of y or some m of n. So if you can go from x to y or y to x, then you say they are in the same orbit. Okay. So we are looking at the orbit of 4. So orbit of 4 has from 4 you go to 6, then 9. So you see you have an equivalence relation here by this. So the set of natural numbers have been divided. With the 4, I have got 4, 6, 9, 7, 5. Okay. So this is one class. So you have an equivalence class formed by this function g. Okay. It just tells you from where you can go where. From 4, these are the only numbers you can go because you have come back to 4, then again it will be 6. Okay. What is the question? The question is this. So this is very easy thing to carry out, do the computation. Now you start with 8. Okay. Instead of 4, I start with 8. Okay. And see where it goes. It goes like this, 2 times 4, like that you continue. Okay. From 8 it will go to 12. You can do. The question is, will it come back to 8 sometime? Like this 4. So, or the orbit of 8, does it have only finitely many points? So whether it will come back to 8 or not. If it doesn't come back, then it will have infinitely many. So start from 8. And do this process. Will you ever come back to 8? That is the question. So we want to have some nice invariant, say from 8, whether we can go there or not. So clearly from 8 you cannot go to 4, because if you are here, you will get stuck here. It is not possible. From 4 it is not possible to 8, from 8 it is not possible to go to 4. They are in different classes. But from 8, can you ever come back to 8? So that's a question. You can feed it to a computer, you can ask to check. You can check it for 1 day, 2 days. You see that it has not come back. but we don't know whether it will ever come back or not. It's an open problem. Nobody knows the answer. Even the best of the computers cannot solve the problem. So, saying you can have artificial intelligence, this, that, but still we have many elementary looking problems which we don't know how to solve. Okay, there are challenging problems. Okay, so with that, this problem is related to something called 3n+1 problem. You can also look it up. So let me, before closing, I just want to give this reference. Almost everything what I spoke about, you can find here. This is an article called Invariants, which I wrote about 10 years ago, and it is published in Resonance. July 2010. So you can search for Resonance. It's published by Indian Academy of Sciences, Bangalore. You may download the articles from, if you go to the website of Indian Academy of Sciences, you can download all the articles, all the things, all the magazines from this Resonance, completely free. There is no charge. There are other websites where they charge, but Indian Academy of Sciences, it is free of cost. You can get not just this article, but you can get many other interesting articles on science, just mathematics, not just mathematics, science in general. Okay, thank you. I will send them.
Thank you, sir.
Because you need a copy, right?
Yes.